In part 1 of the video on single pole power converters, we looked at the basic operation of single pole based power converters and analyzed the buck and the boost modes of operation. In this part 2, we look at the high frequency analysis leading to expressions for the peak to peak ripple in the pole current. And we'll also look at a few numerical examples. Very often you are interested in finding out what is the peak to peak ripple, the high frequency content in the inductor current. So for several reasons. The primary reason is to be able to design the value of this inductance to achieve a certain limit on the inductor current ripple, or in case of motor drive, to find out what is the distortion, the high frequency distortion in the line current that we feed into the motor. So we can make use of the superposition and the high frequency equivalent circuit to determine this to determine an expression for the peak to peak ripple in the inductor current. So this represents the actual complete switching level model of single pole based power converter. So this is actually a transformer model, but the turns ratio is not the duty ratio, but rather it is the instantaneous Q, the switching signal. Okay. So, but QA, the switching signal, can be thought of as two separate quantities. One is the DC value or the average, and the other one is the high frequency content. So therefore, we can split this complete switching level circuit into two equivalent circuits. One is the average circuit, and the other one is high frequency circuit that I'll show later. So if you look at the average circuit, then so the turns ratio here is the first part of QA. So the QA average is the turns ratio, and the other quantities are governed by this turns ratio. Okay. So all of these are average, and we'll get the well-known steady state equations that we looked at earlier. But what we are interested in to get the switching frequency ripple is the high frequency equivalent circuit as shown here. So here, first thing to note is the turns ratio for the transformer is the second part, the QA high frequency part, which is nothing but the complete QA minus the average QA, okay, which is the turns ratio for this transformer, or this current source is this turns ratio times secondary current, and this voltage source is the same turns ratio times the primary side voltage. Okay, that is first change. The second one is this being a high frequency circuit, the DC source, which has no high frequency component, is considered as short circuit here, and another smaller and also the E sub A is also a DC voltage source with zero high frequency voltage content. Therefore, that is also a short circuit. Okay. Then a small approximation is that the resistance RA is considered negligible compared to the high frequency switching frequency impedance of the inductance. So as is given by this inequality, 2 pi fs LA, which is the impedance of the L at the switching frequency, is much larger than RA, so RA can be neglected in the high frequency circuit. So we can make use of this circuit to determine the equation that we are looking for the peak to peak ripple in the inductor current. So this is again the high frequency part of our model, and if you look at the secondary voltage, which is actually same as the inductor voltage VL. So in this it has two components. The Q is the switching component, and QA bar is its average value, which we saw earlier is nothing but the duty ratio D sub A. So when Q is 1, which is the on interval, then the secondary voltage, same as the inductor voltage, is 1 minus D times V sub D. Okay. So that will be Vd minus D times Vd, or Vd minus VAN bar, because D times Vd is VAN average. Okay. So during the on interval, the inductor voltage is Vd minus VAN average, and during the off interval, Q is 0. Therefore, the secondary voltage is nothing but minus D times Vd, or minus VAN average. So that is this magnitude, a negative value. So once you know the inductor voltage, then we can draw the inductor current in the high frequency sense. So that is this current waveform. So it is rising during the on interval at a slope of Vd minus VAN bar, and falling during the off interval with a slope of minus VAN bar over L. And you can add this high frequency content to the average value of the inductor, which is obtained by the other average equivalent circuit, and we can add the two, superimpose, to get the complete inductor current. So as I said, the objective of this slide was to get an equation for the peak-to-peak ripple in the inductor current. So the peak-to-peak ripple, delta I, is defined in this figure here. It is the difference between the peak-to-peak variation in the high frequency IA ripple waveform, as indicated here. So to get an expression, we can make use of the VA relationship for an inductor. L di over dt is VL, and if you consider this during this on interval t on, so then LA here, and then the change in IL is delta IA by your definition, changes from this lowest point to highest point, which is a total change of delta I. This change in time dt during that on interval is duty ratio dA times Ts. So that is this small time dt, and that is equal to the inductor voltage, and VL during that on interval as seen from this waveform is Vd minus VAN bar. Okay. So that gives us the required equation, where the delta I is this Vd minus VAN bar minus dATs over LA. We can also rewrite this by substituting VAN average to be dA times Vd. Then we get the expression in terms of VAN average alone, not in terms of Vd. Okay, let's do a simple example problem that involves a steady state analysis of a single pole power converter. The DC voltage 100 volts, this EA, which could represent the back EMF of a DC motor, or it could be another battery of 80 volts. The filter inductance is 500 microhenry with a series resistance of 1 ohm, and we are considering 20 kilohertz switching frequency. So the problem is for two cases, for the current I sub A to be 10 amperes, and then case B IA to be negative 10 amperes. We need to calculate what should be the control voltage VCA that is given from the feedback controller, and what is the resulting duty ratio under each of these two operating conditions, and also calculate the peak-to-peak value of the inductor current ripple that we determined equations for in the previous slide. Okay, so we'll start with the average model, which is as shown here. And if you are interested in the steady state analysis, DC steady state analysis, the inductor is a short circuit, so we can use that to get the average. We can use that to get the basic duty ratio, because the average currents are given. For case 1, it is 10 amperes. So we can write KVL around this loop. So in steady state, VAN, which is D times Vd, is EA plus IA times RE, just by KVL around this loop. So substitute the numbers. The current is 10, the resistance is 1 ohm, this is 80 volts, so you get VAN to be 90 volts requirement. So to get 90 volts VAN by transformer principle, and given that this is 100 volts, then the turns ratio D is simply 90 over 100, or 0.9. We are also required to calculate the control voltage VCA, and if you recall, their relationship between D and VCA is D is 1/2 plus 1/2 of VCA, from which we get VCA to be this expression equal to 0.8 volts. Okay, and recall that VCA can vary from -1 to +1, whereas D can only vary between 0 to 1, and both are consistent. Finally, the peak-to-peak ripple delta IA, as per our derivation, it is VAN times 1 minus dTs over L, and VAN for this case is 90 volts, D is 0.9, and the TS is 1 over the frequency, 1 over 20 kilohertz is 50 microsecond, and L is given as 500 microhenry. So the peak-to-peak ripple is 0.9 amperes. For case 2, where we want the power flow to be reversed, the current to be reversed, and it's actually negative 10 amperes. So for that same procedure, just that the values would be different. So calculate the required VAN, and that will give the value of the D for this new case. So again, from KVL around this loop, VAN is EA plus IA times RA, just that IA is now negative, making VAN less than the previous case, 70 volts instead of 90 volts. So then D is 70 over 100 or 0.7, and VCA, again using the same equation, comes out to be 0.4 volts in this case. So then the peak-to-peak ripple, same equation, but both VAN and D are different. VAN is 70 and D is 0.7. So if you use those values, same frequency, same L, you get 2.1 amperes peak-to-peak inductor current ripple. The second example involves a transient analysis for the same exact converter, same exact parameters. Now we're actually studying the duty ratios that we derived in the previous steady state example. We derived 0.9 for positive 10 amperes and 0.7 for negative 10 amperes. So those, so initially D starts with 0.9, and at 5 millisecond, there's a step change in D going from 0.9 to 0.7. So we expect that once steady state is reached, during the 0.9 D, we will eventually end up with 10 amperes average current, and eventually when we reach steady state after D is changed to 0.7, we'll have negative 10 amperes, and there will be some transients in going from the positive 10 to negative 10, and the objective of this problem is to actually capture that transient. Okay, so here are some key points that we discussed. A single power pole is by itself a full-fledged power converter. It can give a 2-quadrant capability with positive voltage only, but bidirectional current. By controlling the control voltage or the D, we can smoothly and continuously control the output voltage anywhere from 0 to the full DC link voltage, VD or VN. So the bidirectional power flow actually gives us 2 modes of operation, a buck mode of operation and a boost mode of operation, which is decided by whether our pole output is more or less than the E sub A, the lower voltage battery or the back EMF. We looked at the inductor current waveform; those are piecewise linear, and we got the expressions that govern the inductor current, and we also derived an expression for the peak-to-peak inductor current ripple. So this single pole converter, on the high voltage side, it results in pulsating current, but on the low voltage side, it results in a smooth output current. This is an inductor current, and that is one of the characteristics of this kind of a single pole power converter. So then in the next video, we will take up 2-pole converters, which have even more numerous applications, and we will consider that in the context of a single phase inverter, single phase PV inverter. So we use the same average model, just that now we are dealing with transient or dynamic analysis, so we cannot afford to short circuit the inductance. It should be present for any dynamic analysis. So this is the expression for VAN average. Actually, there should be a bar on top here to denote average. So that is VD times D of T. D of T is this waveform, which is mathematically 0.9 U of T. Then it goes to 0.7 at 5 milliseconds will be minus 2 U of T minus 0.005 5 milliseconds. Okay. So that times VD is this expression. Okay, then we can use Laplace, because this is we need to write the differential equations, and we do that. We solve that using Laplace transforms. Okay. So the Laplace transform of IA of S, the inductor current, is VAN minus EA divided by this impedance, which is RA plus SLA. The expression for VAN, Laplace for VAN is 90 over s minus this 20 over s times e to the minus s 5 milliseconds. EAS of course is 80 over s. Okay. So we can substitute these values in our equation for IA to result in this Laplace equation, and eventually take the inverse Laplace as shown here to come up with the time domain expression, transient expression for the inductor current. Okay, so this is the after partial fraction, this is IA of s, and the inverse Laplace of that was 10 1 e to the minus t over tau, where tau is this time constant LA over RA, and for the given values it was 500 microhenry over 1 ohm gives you 500 microseconds. So I went ahead and simulated this circuit in Plex. So these are the results. So I did two things. One is I simulated the actual switching circuit, and that is this green waveform. Then I also wrote the same equation in Plex, and then got the expression which is given, got the waveform which is this red waveform, and you can clearly see that they match very well, meaning our analysis as well as our transformer, ideal transformer model, they are correct. Also notice that this peak-to-peak ripple during the region when we had positive current and D of 0.9. So this peak-to-peak ripple is much less than the peak-to-peak ripple corresponding to a lower D and negative current. And that's exactly what we derived earlier. So this was, I think, 0.9 amperes peak-to-peak. This was more than 2 amperes peak-to-peak. Okay, so they match very well.